Hi, everybody. Greg here with Scynce, Director of Cultivation Sciences at Scynce LED. Got you guys here today to chat a little about optics. Our optics specifically, why they're important, and of course, why they matter. So with that, let's hop right in. I'm going to share my screen with you real quick. All right, so hashtag optics matter. You guys will hear us say that all the time. Optics are really important, and we kind of hang our hat on our optic throw. It's really important to get the growth that you guys are looking for, and why you can do some neat things with Scynce products that you can't do with other lights on the market. It also can be a bit of an explanation point. It's a deep dive into how light works, why we're getting at some neat tricks that other companies aren't getting at, and can cause a little confusion. So I'm hoping to clear some of that up today. This is going to be up on social media. It's going to be up on YouTube. It's going to be up on Instagram. Wish I could answer these questions live, but if you guys have any questions, please science.cultivation, shoot me a DM, leave the comments here on YouTube. If this is on YouTube, let me know what questions you guys have, any further explanations you might need, and I'll try to get with you guys. So with that, Spectro here is going to lead us on down the road. So first slide, a little quick refresher on lighting terms here. We're going to start with the older terms. We're going to skip over all the lux, lumens, and all that really old lighting terms that's not really used for plants anymore anyway. Shouldn't have been in the first place, but we'll dive into the first oldie, the oldie but the goodie, the PAR. You'll still hear PAR used quite a bit out in the world today. PAR is of watts of photosynthetically active radiation per meter squared. So PAR is an older term. It's been kind of changed over the years on what exactly that range is for PAR. Been expanded down into UV and out to the 730 nanometer ranges, even beyond. So we've kind of moved away from PAR just because it's a little too specific, and it's kind of muddy on what it applies to. So you don't see that much anymore. So what you see more often nowadays is the PPF. PPF is a strange term because it can kind of get muddled a little bit with the next term, PPFD, and we'll kind of jump into that here in a second when we get to PPFD. But for now, PPF, photosynthetic photon flux, that's micromoles per second. So that basically is getting at how much light is this fixture producing? How much light is being thrown out by this light? What am I seeing production-wise as far as active, photosynthetically active light produced from this fixture? It's a good term to know, but it leaves some things to be desired. It's a bulk measurement. It doesn't get at what's actually being applied to your plants, what's being applied to your plants, what the quality of that light is. So it's not the best term to use as a pure PPF term. But it's good to know. Anytime you're talking to a lighting company, looking at a lighting company, PPF will be there. PPFD is what we at Scynce like to use the most often. The thing about PPFD is that's photosynthetic photon flux, same as the one before, but that D stands for density. What does density bring to the table? What density brings is that's a density of per meter squared. So a density area, density, think of density as an area term. So you get micromoles of photons per second per meter squared. Why is that important? Well, per meter squared brings into the area that you're lighting, brings into how much plants, how much area, how much table you're lighting. So it's a really important term and really important to delineate that PPFD from PPF. Now, it turns out that some of the older white papers, some of the older research papers out there, they used to use PPF and PPFD kind of interchangeably. And the best way to tell which one of those you're looking at or reading when you're reading some of these older papers is it'll be expressed in that per meter squared. So if you have a unit with a meter squared behind it, then that's going to be PPFD. If you don't have that meter squared, then you're talking PPF. So the reason we like to talk PPFD is because you get the amount of photons, You get the time those photons are applied and the area they're applied over. So all really important things to know when it comes to growing plants. Second term to kind of dig into here, we hear it quite a bit, is the inverse square law. So basic idea here is you have a source of energy. In this case, it'll be a lighting source. As you move further away from that lighting source or any energy source, that energy will become dispersed and it'll be less energetic. So the further away from that source you get, the less energy you're going to have. Pretty simple term. I think that we can all kind of understand how that works. The graph here on the left shows a single plane A being impacted by single points of energy. And that's how each one of these are measured. And you can kind of see as it broadens out over an area, as we increase those squares, you can see the less energetic as it moves further away. So that kind of brings us back around to PPF. PPF, that F is for flux. So that's an amount of time. So we know how much that light source is emitting in a second, in a minute. We understand that. The flux density, that FD, what that gets at is the amount per area per time. So that really brings those two concepts together. So when you're looking at the inverse square law, that applies to a single point. So that applies better to PPF than it does PPFD, because as the area changes, those points are going to change on where they're intersecting. To get at that, I've made a little graph here basically that shows this bottom line here is the plane that this power source is going to intercept. Okay, so that's where the energy is going to hit. That's the plane it's hitting at. Well, if that plane is 4 feet away from that source directly underneath it, you're going to have a number of energy that's hitting that. Anytime you increase the angle from straight up and down, away from straight up and down, you add distance to where it's going to hit the plane, because as you add an angle, that energy, the 4 feet, you're not going to intersect that plane anymore. So in order to get to that same plane that you want to intersect with the energy, that line has to get longer. So according to the inverse square law, there's going to be less energy impacting that plane because you're further away from the light source. So really standard, most of these lights make that Lambertian pattern, and that is extremely true. If you're directly underneath the light, more energy. As you move away from the light, less energy. So what we've done here at Scynce to kind of pull at this, and this is a really good representation, it's one of my favorite graphs that we have, to kind of show what we're trying to do with our optics. You'll see in the background there that kind of dotted line. That's what was known as that Lambertian pattern. That's known as how the light's thrown out from a bare diode, no optic, or HID, HPS, CMH, any of that kind of stuff, light source. It's going to be thrown in a balloon out at equal amounts away from the light because it was produced at a single source. What we've done with our optics is we have our 120-degree conic optic and our linear 70-degree optic. Both of these are there are optics. The 120 has some really cool patents around it, some really cool tricks that it can do. So these are Scynce distribution curves. This is not true. There's a lot of other optics on the market, 120-degree optics, other optics. These curves only apply to the lenses on our lights. Not all optics are the same on all fixtures. So really important to keep that in mind when I'm talking about these throws. It's specifically Scynce optics. So you'll see there, the dotted line on the outside, Lambertian pattern, no optics. Right in front of that is our linear 70-degree optic. And you'll see that that kind of got a similar shape, kind of a bulb kind of throw, but there's still a little bit more energy. It's a little more focused. You still have that flat line at the bottom where it's driving down in, but you have some kind of sharp edges to kind of increase that energy. On top of that, you have the conic 120-degree lens, and that has a distribution that we like to call our batwing distribution. That really takes that energy and really puts it out on an angle. So your biggest point of light isn't coming out directly beneath that optic. It's actually coming out at an angle next to the optic. So we're kind of working on this inverse square law on how to get that reduction of distance with an increased energy. So if it's applied less underneath and more at the angle, you're making these two even, because on that last slide, as we pointed out, distance away from the source matters. So here's a better look at that. I know that's kind of a weird concept to think of. Just kind of think about those last throws while we're talking about this. So on the screen here, you have a bare LED at 24 inches, and you have the Scynce linear 70-degree optic. The 70-degree optics are on the Dragon Alpha. Those are our high bay application light. So we didn't disperse that hotspot quite as much as we did with the 120s, because we know these lights are going to be hung high. So we need that drive of energy down into the canopy. We want to make sure that it's nice and evenly lit. What you'll notice here between the bare LED and the linear 70 is that secondary cone there, that 70% energy cone. You see on our linear optics, that cone is much bigger. So instead of a real mildly wide band at 90%, and then this head, a smaller band of 70 and a small band of 50%, and then a big band of 30%, you're getting much more of that 70% energy produced where you need it, spotlight over your canopy. So you're not getting the hot spots quite as much, and you have a much more even energy field at that 70% production. You can kind of see the Lambertian throw pattern, hot here in the center, weaker as it disperses out. A little different with the 70. There's still that red spot in the middle, but as it disperses, look how wide and even that energy is coming out from that optic. So real nice energy distribution, kind of pulling apart that inverse square law and trying to get at how to increase that energy on the angle. A lot of our patents are based off of increasing energy on the angle away from the source of light. So again, here with our 120-degree optic, and this optic is really, to me, the coolest one that we've designed. So again, bare LED there, big red spot in the middle, especially at 12 inches away from the canopy, really close to the canopy with a bare LED. Most people probably wouldn't attempt to do this. I've seen crazier things, but really, really close with this. This is why a lot of those bare LED, you get the boards, you get the multi-bar lights, those need to be hung high away from your plants, because that red cone that you're seeing there is the majority of the light. When you look over at the 120-degree conic there, you start to see how that increased energy on the angle works. Directly below the light source, we're talking about 50% energy. So not a ton, not red. You don't see any red in that throw at all. We've taken that red and we've softened it out to a whiter 70%, more even. You're capable of getting these lights a lot closer to the plants, because you're not getting those crazy high numbers of PPFD just blasting away. So really a smooth, even cone. You'll see the energy that's at 50% outside of that is even smaller. So a lot of that energy produced by the diodes at that 70%, real even spread. What that allows you to do is get these lights a lot closer to the plants without burning your tops and still lighting the inner canopy. A lot of people have been growing with LEDs and HPS for a long time. And the first thing that we always want to do is hang everything high, because that's what we're used to doing. These lights are designed to be in racking systems. They're designed to be intense. They're designed to be close to the plants and gentle on the plants, so that you're getting a nice, even distribution, not getting any weird peaks and valleys. The Cush itself is a 3-bar light, so you're getting this distribution in between the diodes on the lens covers, and then also in between the bars. So that's what allows the Cush PPFD map to be so even and butter smooth, because these optics play with that 70% energy. So again, the most energy straight down 4 foot away from that plane, high energy. As that distance gets further away, it's going to have less energy. So how do you get at that? Increased energy on the angle, right? So here we go. We got 100 U moles coming straight down at a 4 foot plane. Inverse square law, you look at that, you assume that next angle over going to have less U moles, it's like, less energy intersecting that plane. So you see on the left there, 175. What we've done in order to kind of break down this rule is we've put more energy on that angular throw. So now you have 100 U moles coming out at the angle and 75 intersecting directly below. That's a much more even throw. and you're not getting that spotlight effect that's just nuking everything directly into the fixture. Really creates that energy field that's nice and even. So get at that even further, here's a couple of PPFD maps. The one on the left is the Raging Kush. The one on the right, competitor light, bare diode, you name it, pretty standard for the industry is when it comes to bar lights, you know, quantum boards, any of that kind of stuff. You'll see a similar throw even with HPS when it's up in the air. You don't see these as commonly for those, but anyway, you'll see the difference here. It's pretty stark right away. When you're in the middle of this bare diode layout, you have, you know, 1100 PPFD right in the center there. By the time you get out to the edge of that light, you're at 257. Okay. So if we go back to what we were looking at here, that's that distribution curve. You get that throw, or it's just going to lessen. The further away you get from directly under that light source, the less light's impacting the plane. Okay. When you look at the Scynce 120-degree optic layout, you can see that 70% kind of look that we were looking at here comes into play. Across this, if you go across the single line, if you do the middle point intercept here at 1056, which is 1100 here, okay? So if I was advertising for this company, I'd say, hey, 1100 PPFD, that's amazing, right? Well, we're at 1050 here, but we're also at 1150 here. We're at 1150 here. So all this energy is getting spread out at the angle and spread to the edges of your table, getting spread to the edges of your plant, just not right underneath the light source. So what that really brings to the table is if you go across and just look at one cross section here, you just follow a line from center 1057 out to 1041. The average on that line is 1040. If you do the exact same thing on any of these bare diode layouts and you go from 1100 out to 257, your average is 705. We need to be worried about how much of this energy is covering how much area. It doesn't matter to me that the middle of this light can hit, say, 1500 PPFD. If the outside of the light is only hitting 200 or 100, that's a huge drop. You're missing so much of your plant. If this is a 4x4 area here, this one doesn't have a metric on what size it's covering, but if this is a 4x4 area here and your plant is 4x4, the outside of your plant is seeing as much PPFD as the center. This is not the case here. You're losing so much power by the time you get to the outside of these. You get leaves on the outside that are barely getting any PPFD at all. Why the center, where we all know, I mean, you can do training, there's super cropping, there's topping, all that kind of fun stuff. But the center of the plant is already going to be the tallest, already going to be the closest to the light source. So why do I need to light that at a higher rate than I need to light the outside of my plants? It doesn't really make any sense when you think about it. You know, it makes more sense to kind of dissipate what's right underneath that energy source and increase what's outside of that direct footprint of that energy source. So this average, the way that we get these numbers so butter smooth is that conical 120-degree where you have more energy being applied on the angle than directly underneath the diode. Here's another look at it. So bare LED, no optics, Lambertian, you see that white area underneath, that's where all the energy is being produced. Outside of that range, less. Normally you'd set up a lights or diodes on a board in an array about like this, where they're going to be next to each other and they're going to be kind of doing what they can with cross lighting and getting those energy levels back up when these parts of the globe cross. Still not the best, most efficient way to light things. The 120, we're back to our batwing pattern that we talked about earlier. Nice and spread. All that energy is kind of coming out to the sides. 70-degree linear lens. It's on the Dragon Alphas, not on the Kushes and the Kales. A little bit more angular, a little bit more straight down. Again, that light's meant to be hung high. So we want some of that straight down heavy energy because we're going to be driving farther away from the light source. So it makes sense to kind of go back to that method instead of keeping things nice and close. When you bring these lights together and these diodes together and these lenses together, what you start to produce is this cross beaming, not cross lighting, cross beaming. And that's really important. As these beams of light cross with this energy increased on the angle, it makes this area underneath super smooth and super even. Same thing here at a little less of a drastic than the 120 on the 70s, where you can see there's some crossing, but it's not quite as smooth. But what happens once these things hit below this plane? Even smooth. It's all about the distance from the fixture. And that's, again, pulling at how these optics work. So let's finally look at some lights over plants, because it's what we all want to see. And as always is, here are our friends in Las Vegas at Medicine. Also, parent company Planet 13. Medicine is their brand. They're completely outfitted with Dragon Alphas at one of their facilities. So they were doing an install on the Dragon Alphas, and they sent this over to me. And you can see the throw on that back wall. It's one of the clearest representations I've seen of this chart. You can see here's the 70-degree lenses. It's exactly what it looks like on this wall. You see right where all that cross beaming is happening up here in this area. And then once you're below, even lighting. And these I mean, you're still with 28 inches, 30 inches here. So that's still way closer than you could get any kind of, single source light, HPS, CMH, single large board, LEDs. So that's really a great look at how that works there. And they've been growing with these lights for a while. They're loving them, obviously. But this is a really cool representation of how that works. So that brings us to the next point. So we're talking increased energy on the angle. We're talking how these lenses work. But what we're also seeing when we create this angled light is we're producing secondarily, it's a diffused light. Because as these things cross and you're producing light at different angles and things are bouncing off plants and they're hitting walls and they're coming back into your plants, and you're passing through that plastic, or through that lens, and plastic is used loosely, it diffuses it. It pushes these photons out in a more mixed pattern than a direct pattern. You'll see here, direct sun, very direct, straight down light, Lambertian pattern. That's where it all comes from, right? The sun is what we're always trying to get back to. Diffuse lights are really common because greenhouse roofing materials do that naturally. Glass does that naturally. Plastics do that naturally. So you get diffuse lights inside a greenhouse. There's no greenhouse on the planet that doesn't grow with diffuse light. On top of that, you can get even more because now you're bringing in atmospheric diffusion, you're bringing in glass diffusion. So you're throwing these photons at different angles even more and more and more. And what this creates is those energy angles start bouncing around the room, and they create a nice even light source. Plants love a nice even light source. It doesn't do them any good to be hot in one area, cool in another. We all know that microclimates, when it comes to this sort of things, are definitely what we're trying to get rid of. So there's also microclimate for lighting. There might be one area in your canopy that's dark. There might be one area that's light. Diffuse light gets at that by creating these bounced and crazy angles and bringing those micro environments of lighting way more even and way more energetic efficiently across the entire area of your plant, not at one single spot. So another great little example here. Here's a diode, direct illumination. You see that there's just a circle right here that's getting lit up, lighter around the outside of that. With the diffusing material applied, you see how even and nice and even that coverage gets. So really trying to get this diffused lighting, and you see again the angles coming out of this diffusing material. And when you've already increased the angle, the energy on this angle coming out of the light, it can shoot this energy further and it can bounce around, and it'll make this even more efficient. So when you walk into a greenhouse, if anybody's ever been in a greenhouse before, it's really common to see bars, strutting, things to hold lights, things to hang equipment from. But when you're standing underneath those bars, you're standing underneath the fans, you're not seeing shadows over the plants. You're not seeing lines from all these bars coming in. That's because of the diffuse light. Because as the diffuse light moves around the greenhouse and bounces around and ricochets inside this glass or plastic area, it gets inside the canopy. You can't stick your hand out and see a shadow because the light source isn't at a single point. It's coming from everywhere. So it's affecting the plants differently than a straight top-down application of lighting. So when it doesn't cause shadowing, you get the leaves that would normally hang over a lower leaf or a bud site or something along these lines, or a fruit. That leaf isn't blocking as much light because you're coming in at all these different angles, and you can dive into the canopy a little bit better. So it's a more even source of light for these plants. So energetically, they're more even, which is healthier for the plants to really emphasize overall growth of a single plant. So, I could talk to you all day about diffuse lights. Here's a great couple of examples of what we've seen out of white papers over the years. Our friend Bruce Bugbee has kind of weighed in on diffuse light here. You can read through this. I'll read it a little bit to you. Given amount of PPFD light that is diffuse may be better distributed within the canopy than a direct light. So a light source that are high in diffuse components should be advantageous to plant growth. Additionally, more leaves would operate below light saturation, thus canopy photosynthesis is more efficient. And that's really what we want to pull at here with this diffuse light and these lenses, is we don't necessarily need to get you more light. We need to make your photosynthesis more efficient, more even. How do we get that same amount of growth with less light? That's what we want to look at. I mean, we all want to get our growth as efficient as humanly possible. When that's photosynthetically, heat wise, cooling wise, anything. It's all about getting efficiency out of these LEDs. So if you can create more efficient photosynthesis, all the better. When the diffuse light component above the canopy is high throughout the entire crop life cycle, as in controlled environments, dry matter production, pull where you will with that, leaves, stems, or dried bud, finished material, can exceed what's attainable in an open field. Now, this is a quote directly pulled from this paper, on the controlled environments paper that they did. But yeah, you'll often hear people talk about, well, cannabis outside or whatever. Cannabis, we'll say cannabis at this one because it's a really high light plant. We've seen that over and over again. Cannabis can take a lot of light. So cannabis in the field, it's hitting 2,000, PPFD a day. We've seen studies that Bruce has put out where, it's running at 1,800 PPFD. Those are numbers that are attainable in the field, but it's not diffuse. It's that straight down, you get a little diffusion from atmospheric, and some of this can be pulled at by why we love, some swear by the sun grown. You get that naturally diffuse light on the outdoors, something that we lose when we move inside normally, unless you have this diffuse kind of lighting distribution throughout a greenhouse. That's why greenhouse grown stuff always has that nice even growth pattern. You don't see a lot of greenhouses with a lot of uneven canopy. They're all pretty even across, and that really digs at this diffuse light argument. Diffuse light penetrates the lower leaves of the canopy better than direct light, again, because of that bouncing around, and it's a more even distribution. So that's why we've seen some things with Scynce LED lights that I haven't seen with other companies. We've seen ratios when it comes to cannabis. If you have an A, B, C grade bud through that plant, normally top being A, B being, mid plant, and C being that what we like to call larvae stuff on the bottom. We're seeing some of those C's go away entirely. We're seeing A and B ratio really come up overall. So you're producing a higher quality flower throughout the plant because of this diffuse lighting, because of the way that it's bouncing around and how it's getting applied to the canopy and really jumping into the inner canopy of these plants. That's what gets us there. And it's a loose term, and it's hard to define. It's hard to wrap your hands around, especially as people that have been growing indoor with these direct light sources for so long. This concept is really important to why Scynce LED works as well as it does to grow plants. So back to this conversation of treating your plants as a whole area, not as a single source. So here I have these, we'll call them barrels, and we have photons coming down directly from the top. What you can see here is this barrel is shaped, as a total 3D area. This single photon may intercept this area and excite it at the level that it's going to. These two might wing right by. They might not even be contacting the surface. If you talk about Lambertian effect, these may be coming out at an angle. This photon may be affecting this barrel over here next to this one. It might not even be intersecting this barrel. So you're going to be missing some photons that are being produced. That's why PPF is a term that's not the best to be used, because if it's producing light, That's fine. But what of that light is actually contacting my plants? What if it's actually getting used to grow? That's the efficiency we're trying to dig at here. So if you angle these lights, if you bring them in, you're getting more of those photons impacting the area, the overall area of your plant that you're trying to affect. I don't really care what my light levels are on my wall or in my aisles. I want to know what my light levels are in a 3D view on my plant, what's actually being collected. So same idea here. If I have these holes on top of these barrels, we'll go ahead and call these holes leaves. We'll say they're leaves. They're the sites that can actually intersect these photons and use them. Well, if you're going to be throwing balls at these barrels that are these photons, it's pretty, which one of these barrels is going to fill up quicker? The one that's missing every other photon that's coming in because it's not impacting this hole directly, or the ones that are aimed to intersect with these holes. You're going to miss a few. It's the nature of the world, but it's more efficient to have them angled, to have them diffused, to have them coming in and intersecting the leaves at all these different directions. Which one of those barrels is going to fill up faster? That's straight down where you're missing the sideways, you're missing certain things, or those ones that are bouncing all over. So this is what really digs at the efficiency of these lenses and the efficiency of diffuse light. The angled light can be intercepted in more areas, and that makes it more efficient. So we've got to the end here, and I'm sure we're all thoroughly bored by now with me talking about lenses and photon applications. So what are the key takeaways? PPFD is the best way to measure energy being delivered to your canopy. Always ask for PPFD. PPF is good, but normally those numbers can be tweaked. So PPFD is what you really want to be looking at. It's what's important. The inverse square law, you'll hear it be thrown around. It's not a great metric to use. As you saw, again, photons are odd things. They're not, it's not a single point. It's over an entire area, which inverse square law doesn't even bring into the conversation. Inverse square law is very much a single point of intercept. So inverse square law, while it's good to know the concept, I mean, it's used everywhere. It doesn't just apply to lighting. Anytime you move further away from an energy source, the less energy you're going to get. But in an area, if you do tricks with lenses and things like that, you can kind of change this law around so that you can use it to your advantage. Secondary lenses. Science has designed a specific set of these secondary lenses to work in a very specific way. Increased energy on the angle to get around these hangups with the inverse square law, to make sure that your light's a little more evenly distributed. There are a lot of lenses on the market. There's lenses in every application, and lenses in office light, lenses in lamps, lenses on cars. Lenses are used. Just really important to know that the secondary lenses that science has are very specific, and they throw light like nobody else's does. Diffuse light in any scenario is a more efficient source of light. It's better. Some companies get at diffuse light by stacking a lot of diodes really close to each other. So as every single one of them are producing this Lambertian effect, they're blending in some of these photons, that's diffuse. But it's not diffuse at the level where you're actually angling the light and causing it to reflect at different angles. So less shade, less lines, less leaf coverage, all coming together from diffuse light. And at the end of the day, DLI is really important, and DLI needs to be measured over the surface of the whole plant. If one area of the plant, again, is getting 1300 ppfd, and this area of the plant is getting 500, the DLI of this overall plant is going to be lower than you think it is if you are only assuming it's getting 1300 ppfd. So if you assume a single spot or a single bright area, you're not going to get the coverage, and your DLI measurements are going to get thrown off and everything else. And DLI, I know I didn't really touch on this in this talk, but it's daily light integral. Really encourage you to check it out on our website. We have a great little map on how it works. You do some calculations, things like that. And I hope to be back with you guys here shortly, and we can do a whole one of these on DLI and really break down those terms and really talk about what it means and what it really applies to over the area. It's all about that area, all about that application area. And we're back to spectrum. So as always, grow deep, grow well. I love sharing this stuff with you guys. I love chatting about our technology. There's some really special stuff that we're trying to pull at Scynce that I really think is going to bring plant health, craft cannabis, quality cannabis, I mean, quality tomatoes for that matter, really to the forefront on what's important for growers, considering these terms that we've been using for years more deeply and introducing some new ones. So hopefully I've gotten your interest piqued. Go out there, pull at these things on their own. There's nothing I've said here that you can't go research yourself, dig in deeper, pull apart, really get the minutia out of this, and really get these concepts, really dive into them, get them really understood, because they're important, and they're left out a lot of the time in these lighting discussions. So with that, I wish everybody the best out there, happy growing, and I hope to see you all again soon.